a glacier was supplied in the industrial era, if most of its ice mass is supplied in the industrial period, then it's going to have more pollutants and release more of them. And this will depend on the climatic setting and mass balance dynamics. Does that answer the question, or shall I explore more the thermal regime?
That was great. Does anyone else have any questions? No? Then I think we move on to the next speaker then. So
thank you.
Thank you very much, Christina, again. So now we're actually changing session. We're going to be moving into oceanography and sea ice. And the first talk here is going to be from Francois Massonnet. And the talk's going to be about the polar region's ideal test beds for data assimilation. And he's coming from the Université Catholique de Louvain in Belgium. And also the Catalan Institute for Climate Sciences in Spain. Sorry. Okay, when you're ready, Francois.
Can you hear me now?
Yes.
Yeah, great. And you can see the screen?
Yes.
Perfect. Okay, many thanks. I have to say that this is my very first web conference where I had the chance to talk. So I think what I will miss most here is the impossibility to know who you are, and the same for you probably. So I quickly put myself into context, and I started my PhD end of 2009, and at that time sea ice was already a very hot topic, because sea ice had been declining quite rapidly in the Arctic, but on the contrary, it had been slightly expanding in the Antarctic. And there has been increased evidence since I started my PhD that both trends might be actually a direct response of sea ice to climate change, to changes in air temperatures in the northern hemisphere and to changes in winds in the southern hemisphere. And today I'm going to ask and answer 3 questions that come out of the figure you have in front of you. The first question is very pragmatic, and it is: can we predict the Arctic sea ice ups and downs? Can we predict these variations a few months in advance? Can we predict whether the Northwest or the Northeast Passage, for example, could be free of ice next September? And for sure, this is the type of information that many shipping companies would need and would love to have to improve planning and management, for example. The second question that I would like to address today is much more fundamental, and it is the next one. So given the observed expansion of Antarctic sea ice surface that we can observe from satellites, what can we say really about thickness or about the volume of ice? And this is perhaps an even more important question, because the volume of ice and not the area defines the total mass of sea ice that we have, and is therefore a much more meaningful quantity to analyze from a physical point of view. The last question that I want to treat today is a typical question that modelers can have, and I'm sure that there might be some modelers listening to me right now. The question is, how can we tune our models? How can we calibrate model parameters as to reduce uncertainty as much as possible in the predictions that we make? Now, for each of the 3 questions, we actually run into the same problem, and I'm sketching here very naively my point. There are many observations of sea ice that we can have from either satellites or from field campaigns or whatever, but unfortunately, these observations that we have will never be enough to describe and to characterize everything we need to know. Ideally, to understand the full picture, we would need to have much more information than what observations can deliver. And this is why models are used extensively, because models can simulate everything, so all the variables that we need, everywhere and at any time. So on the sketch, you can see that the satellites could at most see what's happening at the surface of the ice, and a guy going on the field could measure ice thickness in some locations. But clearly, to have a big picture, to have a full understanding of the system, we need to complete these very sparse observations with additional information. And this problem of filling the observations that we have with models can in fact be formalized mathematically. If we have some idea about the probability density function of what we can observe, which is shown as the blue bell curve on the right, if we have this PDF together with a probability density function of everything we need to know from a model, for example, then there is exactly one unique way to generate the best estimate of the state of the system that we are studying, and how to move from the thick purple line to the orange dashed line has a name, and this is called precisely data assimilation. In other words, data assimilation is the art of feeding a model with incomplete observations as to return an estimate of the full state of the system, which is at the same time less uncertain than what we have with a model, but also closer to reality. So this is really the concept of data assimilation. Now I'm reviewing my 3 questions from this angle, and the first question that I asked was, how can we improve seasonal sea ice predictions? And what you need to know here is that to improve our predictions in summer, so to make skillful predictions a few months in advance for the sea ice, in fact, we would need to know in great detail how thick the ice is in the preceding winter, because the thickness of ice is the variable that holds a great deal of the memory of the system. But unfortunately, thickness is not easily observed from space, so we need some workaround. And this is exactly what data assimilation can offer us. Let me now show how this works in practice. So imagine the following situation. We have an area here in the Arctic Ocean where we have ice, and a satellite is passing